Okay, hi everyone. So this is a review for chapter 5 revision quiz. So based on your responses, I think the question that we need to discuss is question 12, question 14, question 18, 19, and 20. Okay, so let's go. Okay, so this is question 12. Two masses, small m and big M, have the same momentum. Kinetic energy of the masses are E1 and E2 respectively. So usually kinetic energy is K, but they're doing E this time. Okay, so what is the ratio of E1 to E2? So let's extract all information that we have. We know that there are two masses. One of them we call it M, the other one we call it capital M, and both of them have the same momentum. So the momentum of small m and momentum of big M. Okay, so this is for small m, this is for big M. And we know the relationship between them is that P of small m is equals to P of big M. Okay, so we also know that the kinetic energy are E1 and E2 respectively. Not a very nice question because suddenly it asks you E1 and E2, but their mass is not M1 and M2. Never mind. So we can equivalently call this P1 and P2, okay, just for our convenience. Okay, so what is the ratio of E1 against E2? So since they're asking for a ratio of against E1 against E2, so probably our ratio, we can get it using this equation, E1 over E2, and from there we can get our ratio. But how should we proceed? We need to find a relationship between something we don't know, in this case E, the kinetic energy, with something that we know. For this case is momentum. Okay, so we need to find a relationship between kinetic energy and momentum. So kinetic energy is P equals mv. Momentum is P equals mv. Kinetic energy is half mv squared. Okay, to relate them, it's actually quite challenging for you, but it's a very common thing among physicists. What we usually do is we add on another square. Okay, we times up and down with an m. Okay, up we times m, bottom we times m. Then after that, what comes out is just mv square. If mv square is actually p square over 2m. So this is the relationship between kinetic energy and momentum. Okay, knowing this thing, we can now relate the kinetic energy with momentum. So now we can see that it's P1 square over 2m. This is small m for case number 1 against P2 square against 2m. This is capital M for case 2. So if we do a bit of rearrangement, maybe P1 square over 2m times 2 capital M over P2 square. Cancel, cancel. We know P1 is equal to P2. That's why this is the same thing. Cancel, cancel. And we are left with M over M. So E1 over E2 is capital M over M. And if we express it as a ratio, it will be E1 to E2 is equals to M capital M to small m. So this is our answer. And from here we know that the answer is this one. Okay, next question. Question 14. Question 14 says two cars X and Y moving at the same speed are acted upon by equal braking force, okay, until they come to a stop. If the mass of X is twice that of Y, the ratio of the distance traveled by x to the distance traveled by y is. Okay, it's a very long question, so let's extract all the information. Okay, two cars, so there will be situation for x and there will be situation for y. Okay, moving at the same speed are acted upon by an equal braking force. Okay, moving at the same speed, so probably we can say that they have the same speed, and we know that Vx is equals to Vy. Then we know that they are acted upon by equal braking force, so we know that there's Fx and there's Fy, and we know that Fx is equals to Fy until they come to a stop. Come to a stop means by initially it's Vx and Vy, finally it's 0. Okay, since we use V as initially, let's just write it as final. Vy final, and we know that Vx final is equals to Vy final, and they are both 0. Okay, if the mass of x is twice that of y, so there's mass of x and there's mass of y, but we know that mass of x is equals to twice of mass of y. Okay, so what are they asking for? They're asking for the distance traveled by x to the distance traveled by y. This one is what we want to find. Okay, so we will know that what we should get later. Let's don't use yeah, it's okay. So we will need to find the ratio between dx and dy. Okay, so they talk about speed and they talk about force and they talk about change of speed. Okay, so if you see there's change of speed involved, and you see there's force involved, then you know that there's distance involved. These few things can sort of give you a hint that you should be dealing with this with things you learn in chapter 5. Okay, change of speed here, it can be change in kinetic energy. And since you know change in kinetic energy, it can be related to total work done. And you know total work done is related somehow to force and distance traveled. Okay, so this is how you should relate everything together. Okay, so since we talk about we need to relate between change in kinetic energy and total work done, probably is a good idea for us to also give a new symbol, which is kinetic energy for x and kinetic energy for y. Okay, oh, it's not just kinetic energy, it's change in kinetic energy that we care about. Okay, so now let's try to figure this out. Change in kinetic energy of x is finally it's 0 minus initially it's half mx v x squared. Okay, and we know this is negative half mx x squared. Okay, change of kinetic energy in the y is again final is 0 because it comes to a stop, half my vy squared. So it's also negative half my vy squared. But we know that vx is equal to vy, but we know that mx is equals to 2my, so we can sort of modify this to become negative half 2my vx. Vx we can probably straight away change it to vy because we want to find the relationship between kx and ky. Okay. So we change it straight away to vy square. So we can 2 negative my vy square, and therefore we know that it's equals to 2 times of change in ky. So our conclusion here is change of kx is equals to 2 times change of ky. Okay, knowing this particular relationship is important because we know change in kinetic energy allows us to relate to total work done. Okay, so now it's time for us to relate it to force and distance. Change in kinetic energy in the x equals to 2 times change in the kinetic energy of the y. We know that change in kinetic energy of the x is basically just work done total in the x direction is equals to work 2 times work total work done in the y direction. And since you know that work done total is the net force, in this case we assume the braking force is a net force, so fx times the distance dx, this one is fy times dy. And once we reach here, we use something that we learned from the question that fx is equals to fy. So what we can do is we can cancel off fx and fy, and now you are left with dx equals to 2 dy. Okay, if you are not sure how to change it to ratio, move it to something like this. Okay, then up, up, down, down. So d in the x, 2d in the y equals to 2y. So this is your answer for this question. The answer should be this. Okay, next question. Question 18. A ball is dropped from a height and falls freely. The gain in kinetic energy of the ball is, okay, they're asking for gain in the kinetic energy, so it's delta k. So let's see what delta k is equivalent to. Delta k, based on your work energy theorem, delta k is equals to total work done. And since you know it's equals to total work done, let's try to see what is the total work done for this situation. We know that we can get work total by finding the net force, the dot product of the net force with the displacement. The displacement is going downwards, so it's time to find the net force. Find the net force, free body diagram, axis. So in this case, it's quite obvious that there's only one force acting on this ball, and it's the gravitational force, or we call it weight. There's no explicit force being stated, there's no string cables, there's no surface, there's no rough surface. So this is the free body diagram. In that case, we know that the work total will be just weight times displacement times cos theta. We know that the direction of motion is in the same direction, so cos theta will become 1, so it's just weight times displacement. And since we know it's equals to weight times displacement, we know that change in kinetic energy is proportional to the displacement, which is basically the distance fallen. So this is the correct answer. Okay, let's look at the other options. Gain in kinetic energy of the ball is equal to the potential energy of the ball. This is incorrect. what you should say is equal to the loss of potential energy, because in this case we say that the change in kinetic energy plus the change in potential energy is equal to 0, which is basically principle of conservation of mechanical energy. Okay, in this case, the gain should be equal to the loss. Okay, so that's why this is wrong. Directly proportional to the gain in speed. Not really. Gain in the square of speed. Why is it the gain of square of speed? Is because change of k is basically half m vf square minus vi square. So this one right here, it's vf minus vi. This is wrong. This is right. So it's the square of speed. Okay, equals to the work done against resistance, against air resistance, but it contradicts here. When it says force 3D, means by only under the influence of gravity. And if it's only under the influence of gravity, means by no air resistance. So in that case, this would be irrelevant to this situation here. So the answer is your first one. Okay, question 19. Okay. Question 19 says you have a mass M, which is stationary on a smooth horizontal surface, and the mass is being pushed by a constant force F, and probably have gone through a certain distance, let's say. Okay, so the work done by the force in the time t is, we know that work done is equals to force times displacement, but they ask you to relate it to time t, so you have to find the s and its relationship with t. So what is the relationship between time and displacement? So for that, you need to review chapter 2. Okay, I'll just be fast and tell you this is the formula you should be using. Okay, now they tell you that mass M is stationary in the first place, means by u is equal to 0 meter per second at first, and there's it's a smooth horizontal surface. Okay, so in that case, since we know u is equal to 0, we can cross this out, become 0, and therefore our displacement is now half at squared. So if we substitute this, then we can remove the displacement and express it in terms of time. Okay, so this is probably the answer, but if you look here, can't see anything which is similar to this. But don't give up yet. You know that acceleration is also equals to, can be related to force with this statement. Okay, you see that there's only force, mass, and time. So you want to remove the acceleration, you want to bring in a mass. Okay, so you know that you want to remove acceleration, you want to bring in mass, so this is probably the relation you need to use. So acceleration is basically just force divided by mass. So if you bring that in, it will be ft squared over 2. The acceleration is f divided by m, and therefore you will get your f squared t squared over 2m. And since that's your answer, I believe your answer should be this. Okay, last question, question 20. Question 20 said there's a body of mass m, and is when being pushed by a force F, move up a smooth incline at an angle of theta. Okay, with the horizontal. So imagine an inclined plane, angle of theta, and you have a body of mass m on it, and it's being pushed by a force F, and you know it moved up, so this force should be pointing upwards. Okay, so this is the situation. So what is the power delivered by the force when the velocity of the body is v? Okay, they tell you want to relate force and velocity to power, so it's reasonable that its power equals to force times velocity. So as you can see, there's no answer here yet, so this is probably not that simple. Since it's an inclined plane, how about we try to draw the free body diagram first? If you draw the free body diagram, we'll see that this thing has mass, so you have weight pointing downwards. Yeah, we should start with axis first. You need to be a good student. Start with axis. Okay, and we know the angle is theta. Okay, then we also know there's normal force, and there's a external force that we apply only allows it to move out the inclined plane, and it's a smooth incline, therefore there's no friction. Okay, so usually when we finish this free body diagram, what can we do? We can probably try to do something in chapter 4, let's say. So we assume this is x, we assume this is y, so let's do a sum of fx, and since it's moving up, we can say there's a uniform acceleration ma. In that case, what you might know is along the direction of a should be this direction. So what I can take is along the direction of a minus opposite the direction of a. Okay, basically resolve this thing, so you get a w sine theta and a w cos theta. Okay, knowing this n is equals to ma. So we can re-express our external force in terms of w sine theta plus ma. To make it slightly neater, it will be mg sine theta plus ma. Okay, now let's bring this back into the equation, because this looks similar to our answer here. Our answer has m and g and m and a, so probably this will be similar to our answer if you bring it back here. Mg sine theta plus ma times v, and therefore our equation will be mgv sine theta plus mav. Oh, here comes our answer. This should be our answer. Okay, so as you can see here, it relates a bit to what you learned in chapter 4. Okay, so don't worry when you see things doesn't happen. You see things that looks like chapter 4, then feel free to move forward and start applying things you learned in chapter 4. Okay, sometimes questions involve different chapters and need to combine the concepts to solve the problem, and this is one example of it. Okay, so that wraps up our review for quiz chapter 5. Thank you very much.